Hello physicists, welcome to our second video on capacitors. Today we're going to start off where we left last time, and we're going to do a little bit of practice to make sure that we really have these concepts under our belt. So you'll remember in our last video we talked about what is a capacitor. And the simplest version of a capacitor is just a conductor, an insulator, and a conductor. That insulator could be a gap of air, it could be some sort of a dielectric, but we are not going to talk about that in this video. The thing that I want to most clearly get across to you is this idea of Q equals CV. The charge on each side of the capacitor depends on the voltage, the potential difference across the plates. And we showed for a parallel plate capacitor that was just a big metal plate, a space, and another big metal plate, that this just depends on the area of the plate and the distance between the two. Then that would give you the capacitance. The C is a quantity that's in farads, which is it has the sort of funny units of coulombs per volt, but we can see what's going on here. The bigger the voltage, the bigger the potential difference that's applied across the plates, the more charge they'll carry. Now remember from last time, the total charge on a charged up capacitor is often zero because you have a plus charge over here and a minus charge over here. So the plus side charge connected to the plus side of the battery, a minus charge connected to the minus side of the battery, and those opposite charges, however, have an electric field between the two plates. And that electric field is where all of this energy in your capacitor is stored. Now, one idea that we introduced right at the end of last video is that you could have capacitors in parallel and in series, and this would change the overall capacitance. So we could go ahead and bundle our capacitors together and get an overall capacitance of that bundled capacitor. So this would be capacitors in parallel, and we had a formula for how to find the equivalent capacitance if you were going to treat that whole thing as one capacitor. And likewise for this. What would happen if you're going to treat that whole thing of these capacitors in series as one capacitor? So we're going to come back and review that in just a little bit. So I want to start out with sort of a, it's a little bit of a thinking question, all right? So it says, look at this picture. We have three circuits, each consisting of a switch and two capacitors initially charged as indicated. So we've got a plus plate and a minus plate, and we have the positive charges on top, negative charges on bottom. Now, the situation now is that after the switches have been closed, in which circuit will the charge on the left-hand capacitor increase, decrease, and remain the same? Well, if this is your first time thinking about capacitors, you might not know what to do next. So we're going to have to think about what extra thing is going to be true once I close that switch. And the thing that becomes true once you close this switch is that the voltage along this wire, after they have a chance, after everything has a chance to settle down, the voltage along that wire is zero. How do I know that? Well, sorry, I misspoke. The voltage across that wire is constant. Doesn't have to be zero, just constant. How do I know that? Well, remember that our electric field in the x direction is given by the derivative of our voltage in the x direction. So if I'm looking and trying to think, okay, there's no current here after everything is settled down, what is my voltage going to look like? Well, I would expect there not to be any changes in voltage along that line, because if you had changes in voltage, you'd have an electric field. An electric field causes charges to move around, or rather to accelerate. And if charges are not accelerating, then your voltage must be constant along that wire. So in this case, if you look at this, we know that Q equals CV. So I actually can calculate what the voltage is across this capacitor at the beginning. So the voltage across the capacitor at the beginning here is 2C times 6Q. So my voltage would be 6 times 2 times QC. So 12 QC. Whoops. I should drink my coffee all before I make these videos. So let me say that again. V equals C over Q. V equals Q over C. You should be heartened that a dumb guy is making these videos, because that means that you too, a smart person, will be able to do this when it comes up to you on your homework. Okay, so V equals Q over C. Okay, so my Q over C here is going to be 6Q divided by 2C. There's my V. And so my V is going to be 3Q over C. On the other hand here, I am also going to have V equals 3Q over C. That's my potential difference across these. This wire is already connected, so that one doesn't have any chance to change. So when I close this up, I can go ahead and be confident that because we have the same potential difference across both of these, and their bottom sides started out with the same potential difference, there's not going to be any increase or decrease. It's just going to remain the same. Now let's say you didn't see how that would have followed. You didn't immediately jump to this step. What could you do next? Well, as it turns out, we know when we close up this switch that the total amount of charge is going to stay the same. Okay, so my Q total is going to be my my Q on the left plus Q on the right. Okay, so this is going to equal my C on the left, C on the right, plus C on the left, V on the left. Okay, we're just using this equation. C on the left, V on the left, C on the right, which would just be C, V on the right. Okay, and so in this case where these two are connected, the total Q we know, it would just be 6Q plus 3Q. So that would be 9Q. And then we could go ahead and realize that the voltages, once we connect up our capacitors, is going to be the same. We know C on the left and C on the right, so then this would be 2C plus over here, so this would be 2C times V plus C times V equals 3C times V. Okay, I'm just taking 2CV plus CV. Okay, and so if I use that, I can know 3CV, 9Q. I can divide both sides by 3C and find that my final V is equal to 9Q over 3C equals 3Q over C. Okay, so that's another way to see that. Notice our voltage does not change. All right, so I'm going to let you puzzle through number 2 and number 3. This is a homework problem, but essentially what you're doing is you're calculating the voltage on the left, you're calculating the voltage on the right. If you connect those two up and the voltage on the left is bigger than the voltage on the right, the voltage will drop when you connect them. On the other hand, if it's the same, the voltage will stay the same. If the voltage on the left is smaller than the voltage on the right, when you connect them up, the voltage on the left would increase. Okay, so there is a sort of intuitive way to do it. You can do it with math. There's always lots of different ways to think about this sort of a problem. All right, now I want to return to the sorts of problems that we were looking at last time because I know that this topic can be a little bit confusing for students. What we're doing is we are bundling together a bunch of capacitors and treating them as a single capacitor. So we have two versions that we're especially concerned with, the capacitors in parallel, where I've taken each capacitor and connected it with a wire essentially to the battery. And since these are all just a wire, the potential is going to be the same on all of these, and the potential difference across each one of those is the same. The potential difference across each one of our capacitors in series is not the same, but the charge is going to be the same. And so we use that to come up to these equations in our last video for the equivalent capacitance of capacitors in parallel and in series. And so today I'm not going to rederive those, but I do want to show how to use them. Okay, so let's review. For a capacitor in series, if we start out uncharged, and some of you who have done the lab already know that this is the sort of thing where you do have to make sure that your capacitors start out uncharged, or you can get all sorts of interesting and screwy results. But let's say we start out uncharged. In that case, the total charge in each one of these wires is 0, and when you apply the battery, all you can do is shift your minus and your plus charge onto the various plates of the capacitors. So because of that, we know that the total charge on each one of these capacitors, I mean the charge on each plate, is going to be the same. And because of that, the equivalent capacitance is decreased for the entire thing. So you would be storing more charge if you simply had one of those capacitors in, and the reason ultimately is that these now have to share the voltage from this battery. So instead of each getting, if this was a 12-volt battery, instead of each getting 12 volts like you would get in parallel, in series you're going to split that 12 volts up among the different capacitors. So let's just look at a very simple example, and I think this is going to clarify it for you if you haven't understood it yet. So it asks, what is the equivalent capacitance of a 2 microfarad capacitors connected in series with a 3 microfarad capacitor, and then asking the question, what is the charge on each capacitor if they're still connected in series to a 12-volt battery? So I've drawn that out here. 12-volt battery, 2 microfarad capacitor, 3 microfarad capacitor. So what does our equation say? Our equivalent capacitance equation here says that 1 over C equivalent equals 1 over this capacitor, 1 over 2 microfarads, plus 1 over 3 microfarads. So I just want to point out to you, that's what this equation said. This sign just means add up as many capacitors as you have in series, and each one of them goes like this, and then there's your 1 over C equivalent. So now let's go ahead and solve this. 2 and 3, if I want to have a common denominator, it would be 6. So this would be multiply both top and bottom by 3 would give me 3 over 6 microfarads plus multiply top and bottom by 2 over 6 microfarads, and so I get 1 over my equivalent capacitance is 2 over 6, so 1 over 3 whoops 3 plus 2 is 5. And then we keep our denominator the same. So it'd be 5 over 6 microfarads. Now there's a lot, some people who, when they're doing this problem for the first time, will look at this and say, oh great, 5/6 microfarads. Is that my answer? No, that is 1 over the equivalent capacitance. So now you have to take 1 over both sides, and you find that your equivalent capacitance is 6 over 5. Okay, so it's going to be 6 microfarads over 5 gives you 1.2 microfarads. Okay, now what's the second part of this question? It asks, what is the charge on each capacitor? Well, remember that the thing defining a capacitor is that Q equals C times V. So now, if we're treating this whole thing as a single capacitor, okay, so we're pretending that's just one capacitor now, and we wanted to find the charge on it, we would go ahead and use this capacitance. So we could go Q equals 1.2 microfarads times, and then the V is the V across this pretend battery, this whole thing. Okay, so it'd be 12 volts. Okay, so I can take my 6 over 5 times 12 volts. So this is going to give me an answer. I've got a micro in there, so farads times volts is coulombs, so this is going to give me an answer in microcoulombs. Okay, so 6 times 12 is 70. 70 divided by 5. I should have done this beforehand. I'll take out my calculator and do it. 6 times 12 divided by 5 gives me 14.4 microfarads. Okay, so what does this mean? This means that I have a plus 14.4 microfarads on this plate, a minus 14.4 microfarads on that plate, plus 14.4 microfarads on this plate, minus 14.4 microfarads on this plate. And because this charge is the same as that charge, this looks like one old big capacitor. All right, so that's the idea that we're thinking of when we have a series circuit. Now, some of your problems that I've given you with series circuits are a little tricky. I'll show you an example. This is a tricky example, and it says, consider this circuit section where you have 3 capacitors in series, and then those are in parallel with another guy. So this is tricky because I know this is just a wire, so this is all of the same potential. And I know that on my right, that is all at the same potential, but I don't know what the individual potential drops are here. Oh wait, they give me some. All right, so they say the total potential drop over 4 is 12 volts, and the potential drop across 1 is 2 volts, the potential drop across 2 is 5 volts, and then they don't give me the potential drop across this one. However, they do give me the capacitance of this one. So this is 0.80 microfarads. And then it asks the question, what is the capacitance of your first capacitor and the capacitance of your second capacitor? Okay, where do I go with this? So, okay, we're looking for the voltage. We want to go ahead and use this information to find the capacitance on this one and that one. Well, what secret piece of information do I have here? The secret piece of information I have is that the total charge on 2, 3, and 1, that Q equals CV is the same. All right? So if I could find this V, I could find out what my, if I could find that V, I could use this to get my charge, my Q3 equals C3V3. That would give me my charge on my third capacitor. Then that charge would be Q3 equals Q2, Q3 equals Q1, and this charge, this Q3, would be C2 times V2. Well, I know what the voltage across the second one is. I know what the voltage, and let's do that for the first one, C1, V1. I know what the voltage across the first capacitor is. And so if I can find this Q3, I'm going to be able to get my C2, and I'm going to be able to get my C1. And that's what I'm looking for. Well, let's see. What other piece of information do we have? Well, we have that this is 12 volts. We know that this is 2 volts. This is 5 volts. Well, let's think about it. If this total potential difference is 12, then the potential difference between right here and right there is also 12. But we know the difference here is 2, the difference there is 5. The difference here is what? Well, 2 volts plus 5 volts plus that extra thing equals 12 volts. What does that have to be? Well, this is 7. Take 12 minus 7, and you'd have to have an extra 5 volts. Okay? So, we know now that this is not a question mark. This is 5 volts. Now, what do you need to do? To finish the problem, all you need to do is you need to calculate your Q3. Then you're going to use that twice because the charge on the third capacitor is going to be the same as the charge on the second and the first. And then you can use your voltages that they give you across the second and the first to find the capacitances across the second of the second and the first capacitor. All right, so I'll let you do the rest of that for your homework. Now let's think quickly about capacitors in parallel. So as we've said last time, the potential difference across each capacitor in parallel is the same. And because it's the same, you are going to get a charge on this first capacitor, second capacitor, and third capacitor independently in this picture, and you would just have to add up the charges if you're going to treat this whole thing as a single big capacitor. You know, all connected to the battery. And so let's go ahead and do the same sort of thing. Let's say if we have a 2 microfarad and 3 microfarad capacitor, what's the equivalent capacitance? And what is the charge on each capacitor and on the equivalent capacitor? Okay, so I've drawn the picture here. You've got a 12 volt battery, long line, short line. You have a 2 microfarad capacitor and a 3 microfarad capacitor. Well, if we use Q equals C times V, we can find out what the charge on each one of these. So we're going to have a plus charge over by the plus side of our battery. We're going to have a minus charge on the minus side. And this is going to be Q equals 2 times 12 is 24 microcoulombs. And the Q on this other plate is going to be 3 times 12 microcoulombs. So Q there is going to be 36 microcoulombs. Now, if you wanted to find out what the total charge on this equivalent capacitor would be, you could just add those two up. Equivalently, we could just use our equation. So our C equivalent is that we were just going to have to add our C1 plus C2. And so our C equivalent in this case would just be 2 plus 3 is 5. So it'd be 5 microfarads. And then our Q on this total thing is going to be Q equivalent, C equivalent times V. So our Q on our entire capacitor, or on this group of capacitors, is going to be 5 microfarads times 12 volts. So that Q is going to be 60 microcoulombs. So the total charge that this group of capacitors is storing is 60 microcoulombs. What's another way that I could get that? Well, I could add together 24 microcoulombs plus 36 microcoulombs. So the charge on this plus the charge on that gives me the total charge. Okay, so the idea of equivalent capacitance doesn't give you a whole lot of new conceptual tools, but it is important in terms of bundling together several objects as one object. Okay, so when I ask you to do this type of problem on your homework, it says each of the uncharged capacitors in figure 2527 has a capacitance of 25 microfarads. A potential difference of 4200 volts is established. When the switch is closed, how many coulombs of charge then pass through the meter? Well, two ways you could do it. You could take the 25 plus 25 plus 25 and find your equivalent capacitance, then use Q equals CV and find your overall charge. On the other hand, you could just use Q equals CV on each one of these and realize 4200 times 25 microfarads is going to give you your charge on this. It's going to give you, again, your charge on this and your charge on that. So you would have to take each one of those charges and add them together, and that would give you the total charge that would go through this switch. So either one of those ways of doing it is correct. They are not really different. Now, the place where this gets a little tricky is that what happens when I have a circuit that's not just parallel or series? Well, what you're going to need to do in that case is identify the places where you have a total, a recognizable potential difference that's equal across a group of capacitors. So like right here, your potential difference is the same across these two capacitors. So you could find the equivalent capacitance of this group, and then you could treat that as a single capacitor, and then find the equivalent capacitance when you take that capacitor and this one. Okay, so that's a little confusing. So let's try a little bit of a more grounded example. So here is a simpler example. It says, this is a homework problem that I gave you. It says find the equivalent capacitance of this combo. So we're going to treat this whole thing as a single capacitor. It says assume that C1 is 10 microfarads. C2 is 5 microfarads. And C3 is 4 microfarads. Okay, so what would you need to do? Well, first you're going to go ahead and try to identify where you have constant potentials. Okay, so these wires are all at the same potentials. Those wires are all at the same potentials. And so if this were just a single capacitor, I could treat this just as two capacitors in parallel. However, we've got a little stick up here. But I can go ahead, I can treat these as two in series and then treat it in parallel. Okay? So for that, those two together, my 1 over C equivalent is going to be and let's call this our capacitor A. So my 1 over my C A is going to be 1 over 10 microfarads plus 1 over 5 microfarads. Okay, so you do what we did before. You find a common denominator, add them together, take the reciprocal, and find out what that CA is. Then, if you want to find the C equivalent of this whole thing, this just looks like two capacitors in parallel. And so your C equivalent for the entire setup will be CA, the capacitance of that thing, plus C3. Okay, so we used our equation once for capacitors in series for the part of this thing that was in series, and then we used our equation for parallel for the part of this that was in parallel. All right, now, there are just two last concepts I want to go over for capacitors. One of them is the energy in a charged capacitor. Now, it's a little bit hard to think about, but because your Q equals CV, if you have a capacitor, as you put more charge on it, the voltage increases. So then it's going to take more work to put additional charge on that same capacitor. So here's our deal. Remember, we have that the amount of energy that you put onto a capacitor depends on the potential times the charge. Remember, V has units of joules per coulomb. So if we're just putting in a little bit of charge, we can take whatever voltage we have at the moment and then add that little bit of charge. However, the voltage depends on the amount of charge that we already have on our device. So I can now put this voltage in terms of the charge itself. Okay, so I used my Q equals CV, and I've said V equals Q over C. So here is my differential work that it's going to take to put a little extra piece of charge on my capacitor. And if I want to find out what my total work is, I'm just going to have to go ahead and integrate that work from 0 charge to Q, whatever charge I have at the end. So when I do that, the C comes out because that's just a geometric factor. That's the capacitance of our capacitor. And then I integrate from 0 to Q, and I get a Q prime dQ. And so when I integrate that, it's going to be Q squared over 2. And then I take the limits on my integral, and I get Q squared over 2C as the work. Now, work equals Q squared over 2C. I could also write my Q as CV, so I could write CV squared on the top. So I would write C squared V squared. I'm putting my Q in terms of CV over 2C. And now I can put my potential energy in terms of the applied voltage. So I'm not going to make a big deal out of this, but I do want you to realize the reason that capacitors are important is A, they provide a way to smooth out currents, but we haven't gotten to current yet, so we'll save that for another day. And then B, they allow a way to store electrical energy. So here we have our capacitor storing electrical energy, and an interesting thing about this expression is that it actually works in many ways. So for instance, if I have a circuit where I have two capacitors like this, I can go ahead and use this equation find the energy stored on my first capacitor and my energy stored on the second capacitor and add them up, and that would give me the total energy that this circuit is storing. On the other hand, I could also find my equivalent capacitance and then treat this as a single capacitor and use this expression to find the capacitance on my individual of the whole circuit in that way. So it works either way. Now the only reason why this is a little bit tricky is that if you have a series circuit, you know, if I have one capacitor after another, the voltage across of the battery is shared between these two capacitors. And when you use this expression, you have to consider the actual voltage across each one of those capacitors, not the voltage across the whole thing, to find the energy on each one. On the other hand, it still works if you consider this as an equivalent capacitor. If you consider those two bundled together, you can still use this equation to find the energy of your whole circuit. So I have you do that this week in lab, and hopefully it's not that confusing once you work through a specific example. Okay, the last thing I want to point out to you is that capacitors can be more complicated than what we've talked about. And in fact, they almost always are. Real capacitors will have a layer of stuff in between their two layers, and essentially what this allows to happen, it allows the electric field between the two layers to be decreased, and thus allows you to put more charge on the capacitor. And what essentially that does is it increases the capacitance of your capacitor. So if you want to look at more of this, this is even a fancier version. It's an electrolytic capacitor, where it's not even just a solid material between the two, between the plus and the minus strips. It's you get a sort of a reversible chemical reaction. I encourage you to watch this video and watch the YouTube presenter strip apart a capacitor. It's interesting to see. Okay, but I think that's enough for us in this video today. What are the things to learn from this? If you group capacitors like a series, and those capacitors are in series, one after another after another, the equivalent capacitors of those capacitors in series is going to be smaller than any one of those equivalent capacitors. This is in series, one after the other after the other. On the other hand, if you group them in parallel and treat them as a single capacitor, so this is in parallel, these are just wires, then this case has a greater capacitance than any of the individual capacitors. And then the last thing I want you to take from this video is that you can calculate the energy that it takes to put the charges on a capacitor, and you can calculate that either as from the charge and the capacitance, or in terms of the capacitance and the voltage, the potential difference across each capacitor. All right, so thank you for watching, and we'll be back soon.